Hi, good morning, everybody. So this morning we're going to pick up kind of where we left off last time. We were talking about CUDA kernels. We had talked about some kind of theory or things. I want to actually go through an example on them. One of the classic examples that's out there is to deal with matrix multiplication. So I figure we'll kind of work up from there and break it down into pieces and talk about what's going on. So when we're dealing with matrix multiplication, let's first kind of consider just in general what the problem is going to look like. So imagine we have two matrices and we're going to do A times B goes to C. So if we were to kind of write this out, we'd have A. I always like drawing them this way because it allows you to get a better idea of what's going on when you're multiplying. You've got a row of A, let's say the ith, times the jth column, and that generates the element ij inside. Now when you're doing this, you're going to step down and you're going to multiply the corresponding parts. Alright, so these are the elements, we'll call these elements k, and then you sum up down this one to generate. So that's kind of how basic, this form is called the inner product form, and this is what you'll see in most books as it goes on. I feel obligated to also kind of cover a little bit, there's different ways you can actually multiply. This is the one everybody always learns, but it's not the only way to work. So I'm going to also cover a second way in just a few seconds here. But I want you to think about where the parallelism of this one's going to come in and what the data requirements for actually calculating this. So in this case, if I wanted to calculate one element, I would need the entire row I and the entire column j that's going on. And dealing with just that element, I would put, say for instance, a grid of ij, and then maybe I put a for loop k that's just going to sum up over those that goes inside. It's often good, as much as we usually show individual kernels broken down to like one matrix or one multiply, just scalar multiply or something. That means you do an awful lot of memory copies for like one operation. Since there's an overhead in copying memory over and back, what you want is a good arithmetic intensity, which we talked about last time. And arithmetic intensity is basically the number of arithmetic operations divided by your memory that goes on. So you want enough arithmetic intensity that it becomes worth it to pay for the copy over and the copy back. So if you're not doing enough work there, it's essentially you're going to waste time. You can actually slow things down by switching to a GPU if you do a bad job with copies. So we want to do the entire sum over j and k as it goes in. But then I can do this element basically independent with these. Now when you do it though, all the other elements in this same row are going to need I, and all the ones in this same column are j. So to get a better memory usage, it is nice to kind of stick them into a common grid together so that you can do the memory copies a little bit better. Alright, so that gives you one breakdown of where it is. And you can see kind of where the parallelism is going to go. We would parallelize off ij, stick them, for instance, inside one block that goes in, for instance, that's going on, to do that area, and we would use I and j as our thread index, and we'd use k to get arithmetic intensity. This is called the inner product form, because essentially what you're doing is, a row times a column gives me an element as an inner product. There's also a form called the outer product form. And this one's a little bit odder as it goes in. But we can actually show it in the same way. So imagine I took my same A and B generates C. But now I want to deal with, let's say for instance, I want to deal with column K and row K of B. So using the same index type notation. Now if you think about it, this is actually happening for each one of these. If I dealt with, row I, column J here, element K, I could sum across all ij's. And what you'll generate from this is kind of a lightweight full matrix. So if I started taking a look at each one of these, I'd actually get, you know, from doing one all the way down to whatever, say there's n of them or something, you'd get a whole bunch of these little lightweight copies, right? 1 for 1, 2, ... all the way out till you eventually hit n of them that's going on. And then I could sum all these together to get my final C that's going in. And that then just becomes an area where this is calculating them completely independent as it goes on until you do the summation, and then you have to deal with the tree. Now, why might I want to consider something like this? Each has their own advantages, right? This one, when you're going through it, I've got each element is independent of all the other elements. Basically, it's at least independent in the calculations, but right, in the memory usage, there is dependence that's going on. And then once the memory area is going in, if I look inside, I'm still doing a summation on here. So then you've got a whole bunch of little trees interior to them. The advantage that can come on in an outer product style form is, if you think about it, this row and this column is never used anywhere else other than in calculating the kth plane of this. So when I'm calculating this times that, nobody else needs that memory whatsoever. So I'm memory completely independent. So I can put it in very fast memory blocks as it's going in to do those calculations. Now the disadvantage comes in that I end up with all these bunch of planes, and then I have to load very large planes to add them together. What's going on? Now, you could theoretically start breaking these in so you build them as needed in one area and use them, but you would have to do some memory transfers inside the machine. At the moment, with all the things you have to do in here, it often works out a little bit easier on most GPUs to do this. Although, as strange as this may sound, this technique is often faster on hosts. So it has a potential, once memory keeps getting larger and larger for the GPUs, as memory gets large enough, this one might actually become better on-site a GPU. So that's kind of where the trade-off goes, but it's at least worth noting there are other ways to do it. The more ways you know how to solve any problem, the more flexibility you have in solving it, and therefore finding whichever technique is going to be best for you. So you just want to be aware of different ones that are out there. That being said, since at the moment that's usually considered the most efficient way to do it on-site, a device, that's the one I'm going to go through.
You said this one's more efficient for a host?
This is more on the host. This one tends to be better on the GPU that's going on. So I'm going to do this one.
But on a CPU, you might want to do
On a CPU, I would definitely do this one. And if the memory gets large enough on the device, the big issue on this one is you need a whole bunch of these kind of low rank ones. And it's really efficient for just-in-time calculation that's going on, which means that you calculate them when you need them. Now, since you would have to do, at least like one warp at a time, and then you'd have to switch them between devices and whatever. Now, technically now on the device, you can launch kernels as sub-ones. So you might be able to take a main kernel so that you can use shared memory. What you don't want to have to do is keep switching from shared to other stuff, to global. But you could potentially launch one where you take, like for instance, 32 Ks at a time, right? 0 through 31, 32 through 63. Take them in those blocks, launch a sub-kernel that it calculates something and returns back just a single plane. Right? And once that gets up to, having calculated enough of those, you can then launch a sub on those. So you can make it so you're never getting more than 32 at a time. And as long as these planes aren't so big that you're exhausting your memory, this might actually become more efficient, but you'd have to use that launching a sub kernel inside there. And that's a little more than a first program. So there are ways that I could see this one becoming dominant, which is why I want to mention it. And I don't see a lot of people mentioning this type of thing inside classic GPU books. You will find this in like MPI program, books and things of that sort. Anyway, so just kind of a useful side of things. So we'll pick up kind of on this one and how we're going to deal with it. Now, when you're doing this, I've got basically 3 indices that's going on. So if I were taking a look at just a host-based program, I'd have something like, for I equals 0, I less than n, I plus plus. Actually, everybody always does ij. I'm kind of not a huge fan of ij. I actually like doing it this way. Row, row. Let me assume that we're dealing just with square matrices. You can obviously change it, but I'll just put width for this as it goes on. I just think it's a little more readable. So we're dealing with the row and the column. So since we're multiplying square matrices, now as a note to this one, when you're going into them, they don't have to be square. The only thing that has to be is that the columns of A has to be equal to the rows of B so that there's equal number of terms when you're summing them up. And the final answer will be the rows of A and the columns of B, which is readily, I think, apparent from this side. But making them all square is actually very common, number one, because you're often dealing with eigenproblems which are square. And you're also, it's pretty typical in area. There are some non-square ones when you get to singular values. But all right, so we've got this part which deals with getting me to the structure here and to an individual element. Then I have to do inside my case. Now, I'll have a sum which will initially be equal to 0, and then I'm going to have to sum over my inner product index. So, in this one, it's both a row and a column. It's kind of not quite as nice of an, so I'm just going to call it the element that I'm summing up over. So I've got my element equals 0, element has to still be less than width. All right. Now I've got to the area where I'm dealing with my individual elements here, and then I want to just say that my sum plus equals, and then I've got my A and row element times B. Element column. And then this will just keep summing up over each one of those individual elements that goes on, and then I can just say the result, C at row column is equal to whatever that sum is. This. And that'll end up summing up over all those areas. So I walk through each of the every row and column inside C, and I sum up all the individual elements using the row element, which gets my IK, times B of the element column, which gives me row K and column J. Now, this type of a setup in our case, we're going to basically take these outer two, and we're going to put these inside our thread index. So inside of our kernel, matrix, null, kernel. Now, we're going to have to pass it, right? So we define double underscore global, double underscore defines a kernel. Now there's inside of CUDA, there's a couple different keywords you can use for when you want to specify a kernel. Global is going to be a kernel that's callable by the host but runs on the device. If you have _device, _, it's a device that's callable from the device and runs on the device. And if you have _host, _, it's a way of specifying that this is called from the host and run on the host. So you can force them to run on the host if you want to by changing that pre-area. After that, it looks just like a normal function definition that's going on. But you have to specify where it goes, because now you have the option to run in different places. So that's what the extra keyword does for you. The __ is used as kind of like a special delimiter that isn't used elsewhere. So CUDA uses it to distinguish its special markers. So we get void, matrix multiply, and then we just pass it its parameters. It's going to want pointers. So let's assume at the moment, I mean, we can do double precision or single precision. For simplicity, I'm just going to deal with single precision. And you'll notice a lot of ones like to do single precision because single precision is much, much faster on the GPUs. And the reason is single precision is what is necessary for graphics. And so, you know, since that's what's kind of paying the bills for the GPU companies, that's where the optimizer are. So double precision, sometimes you will have to use it, but realize you will not get the same speed up you will with single precision. So you have to think seriously if you're going somewhere else. As I mentioned last time, D_ is not a requirement, but I think it's a good idea. So that means it's going to be a pointer on the device. Pointer, the memory space for the device and the memory space for the host are different, but they're going to use the same numbers. So this is just a sanity check for you. I like using D_ and H_ to separate pointers to each individual one that's going on. That being said, if you read some of the books, sometimes they'll just put a D without the underscore at the beginning. Sometimes they'll put the D at the end, or _D or just D at the end. So, but almost everybody does a D somewhere. All right, so we're going to need our two ones. We've got A and float star _B. And then I need an int. I need to know how big this is. All right, so I've got this whole basic setup. Now once I get in there, I need to know, essentially first replace these two columns that's going on. So I'm going to do that by getting my thread index. So I'm going to declare an int, and my row is equal to the thread index. And column is so I just use thread index. So when you run these kernels, the kernel's going to launch a bunch of threads. Each thread knows their number. So the numbers are always specified in a three-dimensional array, which is X, Y, Z. So just think of it as just a standard struct. So you're going to have inside, you have a block which has X and Y and Z. Now, in theory, X, Y, and Z, if you're just looking at it mathematically, it could be any size they want. But Z is kind of like a subordinate dimension. Since GPUs were really optimized for graphics, X, Y is going to be your graphics plane, which will be huge, that's going on. Z is your buffering that's going on. So it's going to be smaller. So you really can't use Z for a full dimension thing. You could use it when we were talking about the planes. You could get a few of them in there, but you're usually pretty limited on how big Z can be. And it varies from each generation, usually lets it be larger, but you're still talking small. So most people just use X and Y because that's where it's really optimized for, and in this case I don't need anything bigger than it. So this is an individual block. Now, each of these blocks is set up inside a larger structure called a grid.
The block is blocks of memory or blocks of threads?
So these are blocks of threads which will have memory associated.
And they're automatically spawned?
So, well, you're gonna specify
Okay.
when you do the calling. So right now, we're going to assume that, you know, we exist here, and you can access, just like I can access my thread number, I can find out what my grid number is, but the grid also is a three-dimensional array. Alright, so, So you can imagine, and then this larger structure of groups of blocks is a grid. Each of these is gonna run on an individual little group of stream processors inside your larger GPU that's going on. Depending on your GPU will depend on how many of these that go. Each of those will run 32 threads simultaneously, which is our classic warp. So this is kind of the, one block is the basic unit you're accessing. And the advantages we talked about last time is when you can stay within some type of a block structure, if you're inside the block, you have shared memory in common. So all the ones inside here have a common shared memory, but it doesn't share it with these even if they're in the same grid. So they can only, at that point, exchange information through global. So all of these have access to global and constant memory, but you can't change constant memory. So any communication goes through global. Global is slower but larger. Inside shared memory, think of it kind of like a cache in that sense. It's going to be very fast. And to an individual thread, you have registers, which is really fast.
What does the warp refer to again?
So it's a group of 32 threads and they run simultaneous. All right, so you, each inside one of these little streaming multiprocessors that's in there, you have the ability to run 32 threads simultaneously. And they're going to operate on different data, but the exact same command simultaneously. So they all get one command, and this is how it gets very fast, is if you think about when we're building our system and you're building the control and it tells it add this or multiply this or whatever, all of these get the same command, so you have a much smaller control structure that's involved with it. So that's how you get things very, very quick, is by sharing those commands, and that's why we're trying to group them off. And, you know, we're in essence specifying what's happening inside one group, and it'll launch as many blocks of these as it needs. So that's where we're getting our indexes X and Y. So in essence, by doing that, since it will launch enough of these, I'm going to tell them the size, I get this basically for free that's going on. Now, that means all I have to worry about is what's going on inside here. So I can specify now, I didn't actually say, I should really probably technically say int sum and int element, but I'm not worried about that. So I guess I'll say it now, int sum equals 0. Then I'm going to want to actually handle this for loop that's going in. And I'm just going to handle it just like a for loop because I don't, at this point, I'm going to sum across the whole thing. So now I'm going to need for, I guess I should say int element. And then element is going to be less than width. Now, when I'm dealing with these pointers in here to handle what's going on inside, I'm going to first pull off each of these individual ones, and I'm going to load them in. And then I'm going to deal with multiplying them. So I would technically also have out here int, temp for A and temp, I guess I should actually do this as float. My temp for A and temp for B. That's going on. So my temp for A is going to be equal to, now that's my pointer that I'm going to be referencing off of that's going on. And I want that one, that's kind of my base address, and then I need to, from that base address, handle the offset to it. So I've got my DA that's going on, and this is going to be done in a linear array as opposed to a square array. So when I'm grabbing these, I'm going to assume that I'm going to take my A, and it's going to take one row at a time, and then stack them along. Which means I'm going to take my row number times my width, and then I'm going to have to add in which element I'm into, which is element. And that'll give me where in A I'm at. And I have a similar thing for B, except this time element is my row. And my column. And then my sum plus equals to TA times B. And then I can just say I. Want B, Z, that. And now I want, the row is based on row, so I'm at row times element plus column is equal to my sum. So this will handle what's going on. So I'm going to, when I'm dealing with this, row and column now have the index. Each thread will calculate a different element inside there, and then I just load it back into these. So I now have a kernel that's capable of calculating my area, assuming that this is the way that I want to go about doing it. All right, now obviously you can shift them around. There are some things you could do, like this is not necessarily, I haven't tried to be efficient at all in this. Now, there are some things you could do that would be better, like for instance, I could take each of these rows and I could add these elements together into another row, and then I could do an intelligent adding. As this is going, it's going to actually calculate a whole bunch of these and then have to sum them. And I haven't made any attempt to sum these correctly that's going on. So really I should come in when it's going on and put in a synchronizing area in here, and then I should specify how my summations are going to go if I want to make this kind of pretty. But this will cover you because the for loop will handle it. But there are ways I can speed this up if I want to use more sub-processes as it goes. But, for loop it will work. It's just worth noting that's not necessarily the best summation technique. It kind of, that's very linear as opposed to tree-based.
Because that was parallelizable as well.
Yeah, there's parallel that I haven't exploited inside here is basically what that point is. And you could do it by forcing that to do all the independent ones first, and then forcing it to do the sum in a tree fashion. But then you've got the barriers, and that barrier is going to create some problems. So now the hardware can't exploit its own parallelism inside there. So this one, either the compiler can unroll it, or the system itself can have some type of a better scheduling technique to work on them. Now, in general, on GPUs, you don't really get good scheduling, because in order to give you the speed, they're sacrificing the control that's trying to exploit dynamic parallelism. So basically, you're trying to expose it yourself. We good? Okay. Then we just come down to how are we going to call this whole thing? Let's assume that I already have pointers that are to the host memory sections. So we're always dealing with pointers. Everything is going to be pointer, pointer, pointer. Now, I mentioned last time that we've got a command called CUDA-malloc. Is that actually readable? This is starting to look faint to me. Get a different color. There we go. So malloc is memory allocation. So when you're dealing with malloc, you always specify a pointer and you specify a size. Same basic situation is going to go on with CUDA malloc. Right. So this is technically a handle. People sometimes just call them pointers to pointers, but you know there is an actual term for that called a handle that goes on. So, and I'm going to specify that this one I'm going to give it my address of, and what did I say I was going to call this? Maybe I'll do A first. And then I need whatever, however big I want this to allocate that's going in. It needs to know how much memory to allocate here. And what it'll do is this pointer will end up with the pointing at the location in memory on the device that's doing it, hence the D underscore part. Which means in advance I need to have calculated both of these. And hopefully I left myself enough room here. So my size in this case is going to be equal to, we said it was a square matrix. So there's width times width elements, and each element is going to be 4 because I did floats. If you did doubles, you'd have to put 8. And then I would need to also declare a pointer float star of D. And you can use the standard pointer thing because it's the same exactly as host memory. A pointer to it is just going to hold the value, which is an address. Depending on whether you tell it to use that address on the device or the host will depend on where it's going to go. Technically speaking, you could take a host pointer and you could give it to the device. It won't give you what you think. It'll look into the device memory at the same address that you should have been looking in the host memory. So you'll get something that'll, in all likelihood, be wrong, but it's technically not illegal.
So we're here declaring a float pointer on the host to.
So we're declaring a float pointer, right? A float pointer is just an integer that's used as an address. Right? Now classically, we've always used those on host because that's all you've had. But now you do have more. Right? So since I actually have more memory areas, it's also going to be numbered from 0 to umpteen. Right? So in this case, it doesn't matter. It's just an address. And where you use it depends on where things it is. So there's nothing that, I could technically take this, and as long as I declare a pointer on the host for it and use it on the host, it'll work normally. And then I could take that same thing and I could stick it into CUDA malloc and declare a thing on the device and use it on the device, and that'd be okay too. So there's nothing illegal about swapping between them. It's just confusing. Anytime you put confusion, there's a high likelihood of error. So it's not wrong, it's dumb, which is probably worse, because wrong will be caught by a syntax checker. But you know, semantic errors are not going to get caught, which means it could propagate down the line and cause you huge problems.
So basically, if we dereference D underscore A, we'd be getting something on host memory, which we don't want.
Yeah. And if you pass it to the device and you dereference it there,
Then it knows.
you'll get something on the device. You know, and if you use it on the correct one, you get what you should get. If you use it on the wrong one, you'll get something, right? You just don't know. Now on the host, you might even get a seg fault because it'll check the memory. On the device, it's not doing all that seg fault checking. So you will get something, it'll treat it like a float, it'll calculate it, it'll send you back an answer, you know. You're just, you know, you're in deep doo-doo. So this is why, to me, it's worth sticking the D underscore and the H underscore. Then we've got CUDA mem copy. Should be a capital M, I believe. So CUDA mem copy just is how do you transfer something that's on the host to the device or device to the host. The first field is the pointer to the destination. Not to the device, not to the host, to the destination. It could be either. So in this case, I want to copy to the device. So what I want to pass to it is the D underscore A. The second one is the source, which will be h underscore a, assuming I had already allocated that memory and have a pointer for it. The next one that you need is like any other mem copy. You have to tell how big the copy is going to be, and then you need to tell the direction. The direction is an integer. No human being remembers what these numbers are. So we have an abbreviation for it, which is CUDA mem copy. And in this case, I want host to device. All one word. Right, and that's just a predefined constant that will take care of that for you. Now assume this is kind of like, think of this as a repeated grouping, right? I declare the float, I allocate, I do it. Now I would have to do this same thing for both D, and assume I did this again for B. Right? Sorry, I'm just being lazy, but I don't feel like typing or writing it again. So I would do that for A. I would do that for B. Now I have to actually call the kernel that's going on. Now I got to remember whatever I called this lovely thing that's going on, the matrix multiply K. All right. So I've got my matrix multiply K, and I now have to specify what's going on. For your own notes, leave a little space there because I have to put some dims. So I first have the dimension of the grid, and then the dimension of the block. That's what we were mentioning before. And this is where we specify the size of those that goes on. So there's a data type that's added by CUDA called dim3. Right? So I've got the dimension of my grid, which I'm going to specify as just 1 by 1, and I've got my dimension of my block, which I'm going to specify as whatever it's width.
That's the X and Y.
That's the XY. Right. So if you only give it 2, it knows you're just dealing by a 2 by 2.
But
And like I said, the Z is a subordinate.
Yeah.
So you've got a constructor that goes on here.
So the dim3 though is just 3-dimensional.
It is 3-dimensional, but since we often only do, 1 or 2, they make copy constructors that will handle just that size. So you have constructors for different size what you pass. So it knows when I pass it 2 that I'm just dealing with a 2-dimensional, which means Z is going to technically get 0. That's going on. But this will actually set up, this is the parallelism that's going on, so that it exploits them. And then I have to pass all these little pointers. So whatever I needed, the DA, right, the DB, right? I passed it I told her what it needs, so now I got to pass it to it. That's going on. So this will actually run the whole thing, and then I got to copy it back. So I have to do my, CUDA mem copy. And now the host is the destination, and the device is the source. It's still size because it was square, and now I have to give it the other direction. CUDA mem copy device to host. And then I have to free up my variables. And then I have to CUDA free, and then I can give it DA. And I have to do that same exact thing. So just like I did for B and C here, I'm going to have to do it for B and C here. That's going on. But this same basic thing, right? You allocate each of your ones and copy them, right? You set up your parallelism, invoke your kernel, and then copy your answer back and free up memory on the device so you can use it for something else. That's going on. And by breaking them into these pieces of how you're transferring, you could, for instance, if I didn't need to copy the answer back, if I was going to do a sequence of kernels, I could do a sequence of kernel calls on them. And so that would be one way I could force one kernel to finish before I move to the next. Or I could do overlapping, right, to copy some things in while it's doing calculations. It's good. So you can force some parallelism there. I can force parallelisms inside there, as we mentioned last time, you know, by actually putting barriers in. But this lets me actually get a basic program outline that goes on, and you can kind of see where it goes on. And the big thing is the little triple chevrons to just specify where your parallelism goes. If you can force things into blocks, it's better because you have shared memory and common to the blocks and you don't on the grid. So, you know, just keep that in mind when you're allocating whatever you're operating on. But if you make these too big, the system can't handle it. Otherwise, you would just throw everything into the blocks. And it depends, you have to look for each, what is your CUDA level and what your card is for how big this can get, both memory and thread count that's going on. And so it's not worth trying to list them out here. It's much easier if you look up like Wikipedia, list them, or if you go to the CUDA developer zone, you can look up your individual card that's going on.
Can you make that dynamic so based off the required outcome?
So you can in advance. So if you took, you know, this type of an allocation, you could specify, it's kind of nice to do like an environment variable area. You make a library, and so you have a constant area that tells you what the card is and what the size is. And then you can, when you're passing stuff here, you can, take that, if you know it's going to be in groups of 32, whatever, you can calculate that, by doing modulo. Things of that sort, pre-calculate what it's going to be and where you go. So I agree, that would be a nicer way to handle it. But as long as you get the basic idea, now you can start looking at what's the good way to automate them. And the reason why I don't like to specify it is in advance, on here, what's going to apply in, I can almost guarantee in a year or two when, we're at CUDA 7 now. By the time they go to CUDA 8, there'll be some cool new feature that's going to add in. The first time they put out a feature, it never works, okay? Or actually, I should technically say worse. It'll work sometimes and it'll be sketchy in the other times, which I think is actually more dangerous because you can use it sometimes and it'll give you what you expect, and at other times it'll just die horribly. But after usually, when you get to the 2.0 version that goes on, what they have works and works pretty well. And so at that point, you're, able to handle things dramatically differently. And they're getting better at how this goes on. And they're usually trying to make it more and more transparent to people, because the biggest barrier that comes in is, in order to really program and do this efficiently, you have to think. Right? You have to understand the hardware, and you have to block it up, and you have to understand memory and processes, which means you really need to have taken a hardware course where you go through processor design and memory design and cache. For computer engineers, that's fine. Depending on, like Baylor's computer science, they actually do have to take a course that goes through organization. So they do get this. And wherever I've been, I've always forced this type of thing to be taught because it's important for computer science people. But it's not generally true that computer science people get this hardware level. So you can run into a problem. If you've never seen this, you won't know how to do it. And so it becomes magic on how you select those breakpoints. Anything that's magic will be done bad. It's just, And so adoption of this has been slower. Now they've tried to make their own nicer one, like CUDA is very low level. If you look at it, I mean, we're looking at individual threads and how do we pull their indices and whatever else. And it's very C-like when it's going through, which again adds in some kind of complexity and ugliness as it goes through. Now, when you take a look at, some of the other ones that are out there, there's some OpenCL that they had pushed for a while, which I haven't seen them pushing very heavily now, which was designed to be object-oriented. And the idea was to remove the difficulty of using, a GPU by automating a lot of this stuff and kind of hiding it from you. And what people discovered is the code ran horribly. It just did not do a good job. So if you knew enough to know how to program at all, you were going to use CUDA. because you could get good performance out of it, and you just weren't. For instance, the K40s that I have on my cluster can give you up to about, theoretically, there's 2,800 threads that can be run at the exact same time. That's not the number in memory, that's the number of stream processors that it has available. So you could theoretically get a 2,800 times speed up. You'll never get that in practice, but you know, if you think about that, running on a K20, which is only slightly smaller, memory's a lot smaller, but the thread count is not a lot smaller, it's still in the 2000s. When MATLAB was out here, MATLAB has their own, you know, invisible to you CUDA speed up thing. And they were advertising that they could sometimes get up to an 18 times speed up on a K20. This is a coprocessor that should be able to get you speed ups up to 2,000. So, I mean, when you're saying, I mean, you're talking 2 orders of magnitude lower than your theoretical number. That's like saying, hey, we can get 1% efficiency. You know, now 20 times speed up when you versus nothing is still better. So for virtually no work, it's a great deal. But if you're looking at what the machine can do, it's a lousy deal. So this is, but we always say MATLAB's a fast way to make errors. Right? You try your stuff, you debug it, you find out doesn't make any sense, and then please don't actually implement using that. It's just a way to prove your thoughts and ideas, and in that sense, it's awesome. But when you get down to it, you're pretty much forced here. So, you know, I agree with you. That is, you know, on our side, we always want to try to, whatever we can, make it as simple and automated. But it's going to have to deal with the low levels at the moment, unless they come up with a great solution to it. So let's see where it goes. So, we good about how kernels can work? Awesome. So that kind of gives a quick rundown of where it is, and it at least ties in some of the memory areas. It looks like we're almost at our time. So I'm going to call it quits for today on this one that's going on. And then we'll pick up next time taking a look at how we can do some performance metrics on parallelization. I believe is our next topic. So thank you all very much. Have a good day.